Should be able to see our slides now, hopefully. Cool. Yeah, so we're the USC Rocket Propulsion Lab, and before I talk anymore, we have a fun video to get started with that really does an excellent job of talking about what we do.
In the Rocket Propulsion Lab, we design, simulate, and manufacture all of our parts in-house.
To even have the opportunity to do this now, when this was something that I made like a career goal for myself, it's crazy. Like, I was a part of that.
I joined the Rocket Lab basically day one of freshman year, actually before even classes started. Why would I do anything but this? This is so cool.
Ready? Let's get started!
Yeah, so we're the world's premier experimental undergraduate rocketry team. We were founded back in 2005 with the goal of becoming the first student group to design, build, and launch a rocket beyond the Kármán line. And that's the boundary between Earth's atmosphere and space at 52 miles above the ground. Since we achieved that goal 2 years ago in 2019, and since then we've been working to move from a space shuttle to space program, where we're able to continually reliably launch bigger and more higher performance vehicles year after year to really push the bounds of experimental rocketry. We're based on this ideology of raw materials in and rockets out. So that means that we get pretty much everything delivered to our lab from scratch. We get raw metal stock, raw composite materials, raw circuit boards, and we pretty much do every step of the build process to produce rockets. And that includes writing a whole lot of code. As I mentioned, in 2019, we launched a rocket beyond the Kármán line. So this vehicle pictured here actually went to space, and that was a huge accomplishment for the lab. And yeah, we're going to talk about some of the ways that code contributed to us getting there. But first, to introduce the four of us who are here today, I'm Mark Stevenson. I'm a senior studying mechanical engineering here at USC. I'm also looking at PhD programs to continue my education in control systems. In RPL, I'm currently the lead of the lab. I also used to be the simulations lead, which is a very code-heavy position. We write all of the code that simulates where our rocket's going to go and how high it'll perform. All of us here have also had some pretty exciting industry experience. So I worked at SpaceX this past summer and I'm returning there next summer. And then also 2 summers ago, I worked at a satellite company called Momentous. And yeah, I also really like baking, hence why there's a pie with a rocket on this slide. I think Emily, you're next.
Yeah, hi everyone. I'm Emily. I'm a senior studying astronautical engineering at USC. I'll also be pursuing my master's through the progressive degree program. So I'll actually be able to finish up my bachelor's and master's in just 5 years. I'm on the structures team in Rocket Lab, and even though we do have a lot of hands-on work, we still also use code to kind of help us get there, which I'll go into in a little bit later. But we build everything that you pretty much can see on the rocket: the nozzle, the motor case, the fins, the nose cone. We pretty much hold everything that's important, such as our avionics and coding software inside. I'm also the safety officer and outreach co-lead, which means I come to awesome events like this where I get to talk to you guys. And then in terms of my industry experience, I also did some research through USC Space Engineering Research Center on solid propulsion. And then last summer, I interned at Whitting Hill Aerospace. And fun fact, the owner of that company is actually one of the main students who started the Rocket Lab, I guess 16 years ago. So that's a pretty cool connection there.
Cool. Thanks, Emily.
Hi everyone, I'm Maddie. I'm a senior studying mechanical engineering, minoring in nonprofits, and I'm also pursuing my master's through the progressive degree program in mechanical engineering. Currently, I'm the simulations lead, so what Mark used to be. And for industry experience, I'm doing research in the Department of Civil and Environmental Engineering here at USC. I've also had a few internships at Honeybee Robotics, NASA JPL, and Northrop Grumman. And I like helping out with everything in lab, whether it's composites, propulsion, recovery, whatever I can get my hands on.
There you go.
Hi everyone, I'm Julia. I'm a junior studying mechanical engineering, and I'm also pursuing my master's in astronautical engineering through the PDP program. This year in RPL, I'm the recovery lead, so getting the vehicles back after we launch them and all that fun stuff. And industry experience, this summer after my freshman year, I did structures and materials research at USC, and then the next summer did mechanical engineering at Honeybee Robotics, and then this upcoming summer I'm going to be doing some work at SpaceX.
Yeah, so that's the team we have here today. Emily, if you want to take this slide.
Yeah. So just before we dive into how Rocket Lab specifically actually delves into using coding and kind of helping us get to reach our goals, coding is also actually a big part of just, at least at USC, our higher education and undergrad experience. I walked into USC not having any coding background. Like, I didn't even know I wanted to do engineering until I was applying for colleges. So I walked in, no experience, not even sure exactly the names of some of them. I was completely new. And so my first introduction actually was through USC education, through one of our classes, which is an introduction to MATLAB. And it was actually really exciting to learn something like brand new. Like, I realized it was the first time in a long time where I sat down and learned something completely out of my wheelhouse, completely new to me. And so that was actually something really exciting. And it's actually become super useful throughout like the rest of my time at USC, especially when you get into industry. And this goes for engineering or honestly, any point. You're going to have to talk to people, right? You're going to have a team, you're going to have to communicate well. And doing that with a ton of words on a slide, a PowerPoint slide, it doesn't always do it, right? It doesn't, people start to tune out, you don't listen very well. So you need to have pretty pictures and nice plots to kind of explain what you're trying to say. And coding actually does a really nice job with that. And so that's kind of where I've seen us use it the most in terms of undergrad, is being able to communicate either results that we've seen from experiments that we've done, or being able to, this can kind of relate to industry in terms of having designs and being able to kind of promote or try and sell them to your bosses or to your managers, and trying to convince them that like, this will work. Here is my results to prove that. And so, obviously coding too kind of helps us solve things that we can't do by hand. And as you progress into your junior and senior times, in higher education, or once you start your career, you're going to start running into issues that are not easy enough to solve by hand, unfortunately. And so coding has definitely helped us in a ton of ways in terms of making those harder decisions.
Yeah, just like Emily, I also came into college with essentially no coding experience, and have really realized just how powerful of a tool being able to code is to do cool things like launch the rocket on this picture. I guess we can talk some about ways we use code in lab, but I'm wondering if anybody wants to unmute or put in the chat maybe ways that they think that we use code. give it a second. Cool. Well, here are just a few of the ways that we do use code. We get a lot of data from our tests and flights that we need to analyze. And when I'm saying a lot of data, I'm talking about hundreds and hundreds of thousands of data points. So there's really no way to process that sort of data by hand. Likewise, things like the parachutes and our flight computer rely on a lot of code to reliably record data from our flights and recover our rockets. Even just designing the rocket, yeah, launch distance for rockets, somebody just said in the chat. Yeah, designing our rockets and predicting their trajectory is what we have the whole simulations team just writes a huge piece of software that helps us predict how high our rockets will go based on what design decisions we've made along the way. And by being able to simulate tons of designs, it's really able to help us pick the best design without having to build 1,000 rockets to get there. We also control some of the machines we use to manufacture parts using code that we've written. And there are tons of other ways. And just as a general invitation, if people ever have questions, feel free to unmute or use the chat at any point in the presentation. Yeah, we're always happy to answer those. We'll also have some time for questions at the end. I already do see some questions in the chat. What programs and languages do you use and what should we be studying in high school to prepare? Maddie, do you want to take that on?
Yeah, so there are a lot of different languages that we use within our lab. MATLAB, which you saw on one of the previous slides, that one's a big one, big computational and mathematical one. Python, C++. I think those are the main ones that we use. Of course, or getting ahead in high school to study programming and coding. I think a lot of languages are pretty applicable to any of the other ones. So like once you know one, it's just a matter of learning how it's written in the other one. But they're pretty transferable. So I think any coding experience you can get in high school will set you way ahead of the curve. Probably, I think one of the big ones are like C++, and I know a lot of people learn, or not C++, Python, and a lot of people learn, I think Java in high school as well. So any language that you can get your hands on is pretty cool.
Yeah, thanks, Maddie. I see someone else, looks like they're answering the how do we use code in lab. Someone's saying launching a rocket into the atmosphere and letting part of the rocket fall down to make it lighter. This is a great thing that a lot of people do. Companies like SpaceX do this, other rocketry teams do. This isn't actually something that we do. We do one-stage rockets rather than two-stage or multi-stage rockets, mainly just because we've got very good at making large, lightweight rockets, which just like the simplicity of that has allowed us to really succeed, whereas adding like the additional like complexity to a rocket to make it multi-stage can just adds a lot of new failure points that we personally don't want to have to deal with. Julia, do you want to take it away?
Yeah, so like Mark and Emily and Maddie were mentioning before, we use a lot of code to make the rockets fly. And kind of the primary point of all of our code when we actually get to a flight vehicle where like all that code is implemented directly is our avionics unit, which is basically, for those of you unaware, avionics is just kind of like a mashup of aviation and electronics, hence avionics. So anything that's like being used on a flight vehicle is typically referred to as avionics, and we're no different. So all of our flight electronics go onto our avionics unit, which is pictured over here to the right. So basically what you're seeing here is, a bunch of PCB boards, which are printed circuit boards, which, like Mark mentioned, we design those and lay them up in-house. So all of the stuff you're seeing here, we physically have made and put together, which is pretty cool. And what this unit does, I have listed over there, two main jobs of it are to collect data and record data during flight, and also to deploy the parachutes to make sure we can actually get this unit and also the entire vehicle back. So we do that using this unit with a bunch of different sensors that can kind of collect the data and store the data to tell us about where we are in the sky, the acceleration, all of that stuff, which we then use to kind of control the state of the vehicle.
Awesome. Yeah, and then, oh yeah, Julia, do you want to go through this first, and then I'll pop back over to.
Yeah, cool. So like I was mentioning, like one of the big roles of the avionics unit and how that kind of code is implemented with the electronics is deploying our parachutes at the right time with respect to when we're launching. So the way we do this is, you can kind of see on that top image there, it looks like a very weird diagram with blocks and all capital letters and arrows and stuff, but this is actually how our avionics team kind of walks through the control process and the sequence of events that needs to happen to make sure that we have good redundancy, so that we know we're going to, you know, send charges to specific areas of that avionics unit when they need to be sent. So like I mentioned before, we have certain sensors on those PCB boards. So particularly barometers and accelerometers are used in order to kind of send signals to let our electronics know, hey, I'm at apogee right now, which is the highest point of a trajectory. I'm at apogee right now, let's deploy the parachutes, which then will send a charge to ignite a couple E-matches, and that will pop the nose cone off, which there is a video of this process in action, if Mark, you can play that. If it plays.
7, 6, 5, 4, 3, 2, 1.
Oh, yeah, that process there happens on the ground when we test it. So we try out the unit in action to make sure that everything's working with it. And then hopefully we can replicate that during actual flight. And that process more or less allows the parachutes to release and, yeah, recover the vehicle.
Yeah, and we've also got a video. I'm going to skip part of it that shows this actually occurring on a launch.
10, 9, 8, 7, 6, 5, 4, 2, 1, ignition.
So yeah, that sound was the parachute deploying. You can kind of see the nose cone popping around there along with the parachute occasionally. This part is sped up a little bit, or it's about to speed up so we can see it coming down together. Yes, it's descending under chutes, and we see if I skip ahead of it. By the time we're getting close to the ground, it's nice and slow and ready to gently back to the ground. Or at least pretty gently. It does a nice bit of a bounce there at the end, but our rockets are strong and can handle that. Before we move on to Emily's section, we have two questions. First, where's your launch site? I can answer that one. We have three main launch sites that we use. The one in this video is the Mojave test area. It's just 2 or 3 hours north of LA up in the Mojave Desert. And this is where we do have a lot of our small scale vehicles, so vehicles that go up to about 50,000 feet. When we do the large space shot size vehicles, the ones that go to like 300,000 or 400,000 feet, There are only a handful of places in the US where you can launch things that high. One is the Black Rock Desert in northern Nevada. And that's the same desert where they host Burning Man. But it's really in the middle of nowhere, and it's a great place to launch vehicles. Another place that we launch out of is the Spaceport America in New Mexico. And this is a facility meant as a commercial spaceport. So other companies use this launch site as well, such as Richard Branson's Virgin Galactic. So that's one of the commercial like space tourism companies. Also a company known as a Spin Launch launches out of there, but that's the site that we've been using more recently for some of our large scale rockets. Another question we have here is, what are your main goals in rocket research? Do one of the three of you want to take that one?
10.
Yeah, I can kind of speak to this. I think based on my like few years in the lab, it seems like the biggest kind of like goals and research goals that we have are just to kind of build off of what we've done in the past and kind of constantly improve all the technology that we've kind of struggled to accumulate over the years. Like, so for instance, like cutting mass down, optimizing case lines, stuff like that. All of those things we like to prioritize trying to test things, and a lot of times we'd favor having an explosion and learning a lot of lessons than doing something, you know, verbatim that we know will succeed. So just kind of trying to push ourselves to learn new things and do cool stuff in the process is kind of the biggest research goal I think we have.
Yeah, we also, of course, really value education. I mean, people only come through this lab for like 4 or 5 years through their undergraduate degree. So really, we try and do what we can to make sure that people enter our lab knowing usually nothing, like all of us here did, and come out being rocket scientists. So it's a lot of work to make that happen in 4 years, but I think we're pretty good at it. Emily, want to take it away?
Yeah, sure. So like I mentioned earlier, I am a big member of the structures team, where one of our biggest layups is our motor case. And so something really unique actually about Rocket Lab is because we've been going on for quite a while now, we've really kept in touch with alumni and those who have kind of made their way out to the industry and have started their own companies and whatnot. And so we're actually really fortunate that we get materials that are composites donated to us. We wouldn't be able to, be as successful as we are without them. So I think it's important to recognize that. But so instead of, one of the big things that gets us so high is that we're able to use these lightweight materials that are known as composites. You see here a carbon fiber with epoxy. And so instead of having a metal case, right, which is much heavier, we are actually able to use these certain materials to have thin and lightweight rockets, at least in respect to, the structures of them. But actually, in order to make these motor cases, we have a in-house winder, which is actually also pretty common in industry. If you look up any sort of a filament winder, you'll be able to find some pretty cool videos that are very satisfying. I highly recommend. But some of our alumni actually built our own winder that actually helps wind this different material around this huge like metal cylinder, and then we stick it into our also in-house oven and let it to cure, and then we pull it out, and it's like as hard as a rock. You can knock on it, and so we actually have this cool video kind of showing it in action for one of our cases quite a few years ago.
It might be a little hard to see on Zoom, but the hole on top of the carriage being the moving part, is wrapping around the case there.
Yeah, it's like we have these like strips of material, almost like a string, or like, at least that's like it's the width of a string almost. It obviously has a lot more strength than that, and we're actually able to kind of wrap it around using this winder. That's through coding. That's through we have original code through Python, and then they create these configuration files and actually help. This code actually helps us translate onto the mandrel what angles we want these like strips of material to lay across. There's actually certain angles that kind of optimize our strength in terms of both stretching this direction, right, and then also in the hoop direction. And so that's a huge part. And it's actually really cool because even though I am on the structures team, and I don't necessarily do a whole lot of coding myself through the lab, our motor case layups is probably one of the biggest times that structures people actually interface with, the software and the coding. And it's really important that we actually understand what it's telling, this winder to do, and how we actually can change the code and alter it to make it do what we want. So even though you might not necessarily be super interested in, pursuing computer science as like your main education or career goal, there's still a lot of there's still things to know about it that can really help you, reach your own goals, whether it's not directly related to computer science. So you can kind of see the cool little design that it creates on one of our finished cases there with the winder finishing up. But yeah, it's a ton of fun. I love it. And it's actually really cool to see all of us, kind of start from scratch. And like Julie was saying earlier, build upon what alumni have started, and kind of find ways to make it better through improving code and finding bugs that they kind of left behind for us, unintentionally, of course.
Emily, how heavy is this case, and how big is it? Just to get people an idea of how impressive this is.
Yeah, this case is what? Is it like 8 feet, maybe 10 feet? I forget how long exactly our mandrel is.
This one's I think 120 because the end effects aren't
120 inches. Yeah. Yeah, so this guy is big. It's hard to tell in terms of, you can kind of see some solo cups lined across the way there to kind of get an idea. But I mean, like, this is for our one of our space shot vehicles, or an upcoming space shot. Or I guess this particular one is for our next static fire. But in terms of lengthwise, it's pretty similar to what a space shot would look like. And Traveler 4 was 13 feet, I think, in total, including the nose cone. And so cases tend to be about 8 to 10 feet, I think. In terms of how light it is, I actually don't have the exact number on it, but I know it's extremely light to where I can pick it up myself. It's only a few pounds, maybe. I think, did we weigh it, Julia? Yeah, or Mark, were you there?
Yeah, I mean, a few pounds, definitely. Which, keep in mind that this is holding in about 1,000 pounds per square inch of combustion gases that are thousands of degrees Fahrenheit. So, like, despite being so lightweight, it really has some incredible properties that allow us to do what we do. Let's see. Sorry, slides are a little out of order here. Already saw this. Yeah, so now you get to hear me talk a little more. So another place that we use code is for data analysis. And one of those main pieces of data analysis is analyzing data from our Kiwi tests. You might wonder why we have tests called Kiwi tests. It's a bit of a joke. These tests are small 4-inch diameter grains that we only ever fire on the ground as a way of seeing how fast our propellant burns. So just like how kiwis are small flightless birds, these are small flightless rocket motors. And I'll just show you what it looks like when we burn 12 of them over a weekend. We actually, this past weekend, we're out up in the desert and tested about 20 of these in a weekend, though our media guy hasn't gotten the video uploaded yet. But still, this is a really cool video.
5, 4, 3, 2, 1, ignition.
Yeah, so that's a lot of propellant burning, and you might wonder, why do we burn so much propellant? Well, we have this equation up here. Don't worry too much about it, but basically it says that the speed that that our propellant burns is dependent on how high the pressure it's burning at is. And our question really is, like, what exactly is that relationship? Like, how does pressure relate to burning speed? So the idea is we burn the propellant at a lot of different pressures. So I think in that video you have a range of about 600 pounds per square inch to probably close to 1,500 pounds per square inch, and we collect tons of data from that. When I say tons of data, I mean we have, that video probably shows about 200,000 data points of pressure data. And like, sure, maybe you can do math with like a handful of data points by hand. But once you get to 200,000 data points, if you want results all quickly, you need to use code. So what we do is we basically turn knobs in that equation until we get good looking results. So that means that we're actually doing calculus on all of those data sets. We're taking an integral of all of those data sets about 250 times. And again, you can't do 250 integrals of 200,000 data points by hand. Like I'd be dead before I was even close to finishing that. But luckily, code helps us test all of these values super quickly. And when I say super quickly, in a matter of a few seconds, we're able to analyze all of this data and estimate how fast our propellant burns, which at the bottom here, these orange curves show simulations based on our final estimate, whereas the blue curve shows the actual data, and they look pretty similar, which basically says we're doing a good job of being able to predict how quickly our propellant burns. You might be wondering, why do we care so much about how quickly our propellant burns? Like, it's like, you just want it all to burn. It's going to have the same chemical energy in it, no matter how quickly it burns. But that's not necessarily true. Here's a video of what it looks like when propellant burns too quickly.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition.
Yeah, so you see that, like, this is clearly not a rocket motor. This is essentially a small explosive device that then catches on fire for about a minute afterwards, which really, well, it is pretty cool. It's not a desirable outcome. Meanwhile, when we do have better data on how fast our propellant burns, we can get things more like this video. Sorry, there's no sound on this one, but just imagine the sound of a rocket motor. I think we have one other angle coming up with some stuff. Finally, a thermal camera view of the same firing, which is pretty cool looking. But yeah, so when we have good data about our propellant and a good understanding of our propellant, we're able to make really cool things like this. And we're really only able to understand our data with the help of a whole lot of code, analyzing a huge amount of data. Trying to go to the next slide. It's not wanting to. Nope. There we go. Maddie, take it away.
Yeah, so once we're able to understand our propellant and have like a successful motor, then we can start designing like what our flight is going to look like. So this is one of the main goals or roles of the simulations team at ArtPL. So as mentioned before, we need code to help tell us our flight performance, trajectory, and our characteristics. So you can see on the bottom, there's a bunch of fun plots. So like the one on the left is showing how high it goes. It's going up to about like 435,000 feet. Mach is in the middle, and that is how many times the speed of sound it's going. So like how fast is it going, but relative to the speed of sound. So it's going 5.5 times the speed of sound as it's coming off the tower and launching. And then acceleration, we're also hitting about 20 Gs off of the tower or at burnout, which is really, really, really fast. I see a question in the chat, how much thrust or power is needed to lift a rocket that high? Mark, do you remember the number off the top of your head?
Our most the one that blew up in the previous video and the other one on the previous slide, those both produced about 2 tons of thrust for roughly 10 seconds, I think 14 seconds. So yeah, 2 tons of thrust for 14 seconds. That's a lot of thrust. It also, of course, you need more thrust if you have a heavier vehicle. So having a really lightweight vehicle like our composites team is able to make for us really reduces that requirement a lot. But still, 2 tons of thrust is a decent amount.
Yeah, so that much thrust, our composites team needs to be able to handle that within our case, and every other team needs to work with that as well. And so like these simulations also help us like size our motors and fins and nozzles. So we need to make sure that we size our motors such that, or like it goes 2 ways, like size our motors so that it'll produce the correct amount of thrust and pressure that we need it to, but also like tell the composites team what we're going to be aiming for so that they can build a case based off of our simulations. And also like sizing our fins to make sure our rocket is stable and doesn't like pitch over when it's coming off the tower. Helps us size our nozzles because like to make sure that we're seeing the pressure that we want it to, we need like the hole that the nozzle's coming out, or the thrust and the pressure and everything's coming out of. We need to make sure our nozzle is sized correctly so it doesn't blow up. It also helps us tell us like where we're going to land. So in the top right, you can see a dispersion area of where our rocket's going to land. So we run randomized trials. So like we change a bunch of different knobs on our rockets randomly, and then to see like where it'll land. Because when you're designing a rocket, it's not going to be exactly how you simulate it. So if we have all these uncertainties, then we can figure out, okay, what's like our best case, what's our worst case scenario, where are we going to land to make sure that we're not going to be hitting buildings or people. So making sure we're aiming it in the right direction and not going to hurt anyone while doing it. It also helps us aim our tower the day of launch. So day of launch, we use like up-to-date wind files from the National Oceanic and Atmospheric Administration. I think that's the first time I've said that right. So we use wind files from NOAA, and then we aim our tower in the direction that we want. So once again, it doesn't come down and hit anyone because the wind does affect it day to day, hour to hour. We also need to make sure that we're not launching in high winds. Otherwise, something like it could go like 30 miles away, which is something we don't want. So flight simulations are super important. This is all coding. Everything we do in simulations is coding. So it's very, very code heavy. So yeah.
Yeah, I see there's also a question which you more or less answered. How does weather affect the launches, and how do I find the ideal weather? The ideal weather would be no wind whatsoever. That would make the simulations team super happy, because then we could do a really good job of predicting pretty much exactly where it would land. If it's too windy, we can't launch because, as Maddie mentioned, you have the risk of pitching over when you come off the tower. So that means like tipping over, and now your rocket is not going up, but going at an angle, and it's going to end up far away. And then like that's bad for multiple reasons. Partially because we tell the government like when we're launching and where we're launching. So if it ends up somewhere well outside of that, they would be mad at us. But luckily we're generally good at doing our jobs, and we are able to pretty accurately tell them what airspace we need. The wind also makes a big difference when the rocket is coming down under the parachutes. If it's too windy, that can blow the rocket really far away while it's descending, which can make recovery difficult or impossible. For example, in the plot on this side, there's a military base just to the right off the picture. So if it lands there, we have to pay a ton of money to get our rocket back, and we might not ever get it back. So yeah, less wind is less wind, clear skies. Those are all things nice for us. At some of our launch sites, we have to deal with like dust storms that come through occasionally, or other like more extreme weather. So really can't launch in that. But yeah. here, let's see, how are we doing on time? We still have like 20 minutes. So here's a nice video that about our space shot vehicle, Traveler 4, that kind of ties it all together. You'll see pretty much everything we've talked about in this video. Yeah, so enjoy.
At 328,000 feet above the Earth, air is too thin to sustain winged flight. Beyond this boundary, known as the Kármán line, space begins. Founded in 2005, the USC Rocket Propulsion Lab has attempted 4 space shots, all unsuccessful. After an extensive development and test campaign, including the record-breaking flight of Fathom 2 to an altitude of 144,000 feet, USC RPL launched Traveler 3 in September 2018. Unfortunately, due to procedural and communication issues, Traveler 3 was launched with its avionics systems unarmed. No flight data was recorded, and no recovery system deployed. Despite this failure, Traveler 3 survived powered flight and impacted intact, proving its design to be fundamentally sound. Armed with this knowledge, USC RPL is moving forward with Traveler 4. Designed, like its predecessor, to travel nearly 6 times the speed of sound and reach altitudes of 400,000 feet, Traveler 4, if successful, will be the first all-student-designed and built rocket to pass the Kármán line and reach space.
In the Rocket Propulsion Lab, we design, simulate, and manufacture all of our parts in-house.
The motor was one of our largest of all time. It's about 180 pounds of propellant.
We follow a recipe that was created over many years. We were able to come up with a propellant that rivals some propellant that's made by like professional companies.
All the PCBs, the structural components had to be built completely ground up. You know, it's exciting because in a way we kind of got to do like a free update.
We're gonna pass this in.
I am powering the hamster unit on.
Peter? This is Connor checking in. We have successfully handed the unit off for recovery. Over.
Avionics unit going in.
We are ready to receive rockets.
Run slow, slow.
All right, Neil here. The truck is rolling out right now. Over.
Woo!
This is Dennis. We are now beginning our go halt checks.
Confirm the air and range are clear.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition.
Kilometers, 9 kilometers, 13 kilometers, 17 kilometers. We are appearing to start to lose lock. Over. We appear to be getting pieces of packets. Over. The drogues are fired.
Drogues are fired. We're in space.
It's always such a
328.
great video. They're not so great though. We're gonna. There we go. Cool. My slides got a little funky, but that's okay. Yeah, so I see a question. What happens to the rocket once it's in space? So yeah, the rocket's in space for roughly a minute. Mainly just kind of slows down and eventually at some point starts falling down to Earth. We get some pretty great videos and data while we're up there. These are all suborbital rockets, so they just go up out of the atmosphere and then come back down through the atmosphere. To actually get into orbit, it requires about 25 times more energy, so a little outside of the scope of what we can do. But yeah, when the rocket is in space, that's when we'll deploy our parachutes, so that as it starts to come back into the atmosphere, we start to decelerate. If your parachute doesn't deploy while you're in space, like happened on Traveler 3, you end up impacting the ground at about a mile per second. And really nothing can survive an impact at a mile per second. So that's really important. And as the video mentioned, like coding is essential because Traveler 3 failed since the avionics unit wasn't armed, like the computer wasn't running the code that it needed to. And without that code, it wasn't able to deploy the parachutes and we lost the entire vehicle. So yeah, coding is important for us when we're in space. Let's see, we've got like 10 more minutes. We can answer questions about anything we had in the slides, our like careers, our education, how we got where we are. Really open to anything.
I have a student question. Go ahead. Has the military ever shot down a rocket of yours?
No, so when we're launching something, we tell the FAA, the Federal Aviation Administration, when we're launching, and that's like paperwork we fill out a few months in advance. Then the day of, we have to call every airport in the area to double check that they're aware of our NOTAM, or a notice to airmen, which basically tells all the airports in the areas, and that includes military bases, like don't fly in this airspace at this time. We are firing a rocket there. So everybody in the government and anybody who would be in the air at the time knows when we're going to be flying. So they don't think we're some like foreign power like launching a missile at the country. Like they're fully aware of us, and yeah, we have to be in contact with them, but they think what we're doing is pretty cool. How much teacher/professor involvement is there in these projects? Do one of the three, do you want to take that?
Yeah, I can speak a little bit about that. We do have an advisor with us through the Rocket Propulsion Labs. His name's Dan Irwin, but he is definitely very hands-off in terms when it comes to our projects. He's a huge supporter in what we do, and he loves to see us succeed, and he definitely steps in when he needs to. You know, when it comes to, he's definitely a huge help when it comes to communicating with the university in terms of just certain logistical things, like what our plans are in terms of when we're launching and what's happening in our actual specific lab space on campus. But other than that, it's very much student run. We make a lot of this happen because we're passionate about it and we love doing it, which is probably one of the coolest things about this lab.
We have another question.
Okay, so I know that you guys are really excited when the rocket actually takes off, but what's like the first thing that thought that pops up in your head?
I love that question.
No, that's a really good question. Like,
I feel like we all have different answers depending on the sub team that we're involved in.
Well, it's funny. I always talk about how because you know we have our 10-second countdown, and throughout the process of making making our vehicles. Like it's never, none of them are ever gonna be perfect, right? Like there's always something you kind of wish you had done better, or maybe checked one more time. And so whenever there's like, at least for me, it was like the 10 seconds, like 10, 9, like every second there's a flash of like one thing like I wish I had checked, or one thing you know, I wish I had done a little bit better. But gosh, like once it actually like goes off, I don't even know if I'm having any like particular thought in my head at the moment. It's really breathtaking, honestly. I mean, like I was only a baby freshman. I mean, I guess all the seniors, yeah, in this room were when Traveler 4 actually launched. It was only like our second semester at USC, and so we knew very little in terms of like, you know, what we were looking at, and it was crazy. I mean, yeah, it really does. I mean, obviously you can tell I'm like kind of speechless when I try and talk about it.
Yeah, there's just like this rumble like through your chest, like you almost can't just like feel anything. You just feel this rumble through your chest of what, like 200 pounds of propellant being burnt in 10 seconds. And like, yeah, it's just pretty incredible to see when it happens. You probably see us all getting kind of emotional during those videos when it launches. Like even now, just thinking back to it is it's just a ridiculous experience. Julia, it sounded like you had something to say.
I mean, for recovery, we have to integrate everything like morning of launch. So I know like the composites folks, like once the case is made, once the structures are made, it's kind of like we've done what we can do, like praying everything goes okay. But for recovery, like we're actively working on it on like minimal sleep, like up until we hand it off for the vehicle to actually get put on that like launch structure you're seeing there. So it makes it a lot more nerve-wracking, I don't know. It just makes it a lot more scary during the countdown, because you're thinking about like, oh boy, I really hope when I was sleep deprived I didn't accidentally fold something incorrectly or forget to tie a knot, like, and then you just have to wait until it comes down and hope for the best.
I see another good question. Do most students go on to graduate school after the undergrad work, or do many get jobs in industry? As you saw, pretty much, I think all of us are doing at least the 5th year master's program that USC offers. As I mentioned, I'm looking at PhD program, but there's definitely a mix. We have a lot of people go through the progressive degree program because it's a great way to get a little more specialization before going into industry. We have tons of people who go straight into industry. Right now, I think we have like 30 alumni at SpaceX, and a lot of them are people who've graduated in the past few years. Likewise, there are a few pretty big aerospace companies like Relativity Space, which was founded by a couple of our alumni. So there's really a wide range of trajectories that lab prepares people for, and there's definitely no one right way to do it. It's a lot about just kind of for people figuring out what their passion and like goals are for their career. I see another question. How long did it take, if I can read it, how long did it take to come up with the code before testing your rocket? I think that's a question that like each sub team would answer differently. For example, the simulations team, which me and Maddie both have done a lot of work with, the simulation software has been like iterated on for I think about 6 years now, something like that. I used to always say 4 years, but now I'm older and it's some longer amount of time. But yeah, so that's code that's been iterated on forever. Things like the avionics system, they've done a physical redesign of the unit over the past couple of years. Yeah, so they kind of rewrite the code to go along with that. Yeah, Sarah, do you want us to wrap up so you can get to the survey?
I can share it in the chat. If you want to continue answering questions, that's absolutely fine. But yes, we would love if you could complete this post survey, if the teachers could give us some feedback about how today went. So I'm just posting that link in the chat right now at whatever time you're able to fill that out. Thank you so much for coming. But if you would like to continue answering questions, feel free. We can end at 10.
Yeah, we can keep answering. I see another one. What do you wish you'd learned before working on this project? Either the three of you want to take it?
That's a good question. I honestly, because again, I walked in knowing nothing. And I don't know if I would change that. I really like it was I don't know, it's my experience, I guess, coming in and being able to learn from like all of like the students above me, and just kind of being able to, I mean, again, it was definitely a little overwhelming at first, right? Like there's so many different pieces and parts have to come together all at once. But I don't know, I think coming in with a fresh mindset and just seeing all these different, like learning all these different things at once was really what made my experience super exciting. I don't know if I had anything in particular in terms of what I wish I had known beforehand, because at that point I didn't even know what I didn't know.
Yeah, no, there's like so much you can learn in the lab. Like I've definitely picked up skills that I never would have thought of, like some of the like electrical engineering type stuff. As I said, I was a mechanical engineer, so it's really the sort of thing where like there's so much to learn that like a lot of times like you just kind of need to experience it all and then start figuring out what you really want to do. I always caution people from like it's good if you're passionate about something, but I caution people like right away saying this is what I want to do with lab, because definitely like a lot of people discover what they're like really passionate about even a year or two into their time at lab and realize, oh wait, like this field that I didn't even really know existed is actually like something I want to spend my life doing.
I'd also add that I fully agree. Like technically for me also came in knowing nothing, and I wouldn't change that. One thing that I wish I would have like kind of internalized a bit more in high school coming into like RPL, or this like applies across the board to any design team or like anything you really do in college, is really just don't be afraid to ask questions, and don't be afraid to put yourself out there and like kind of learn anything you're interested in. I think those are like two things that are more soft skills, but really will kind of like take you that extra mile for anything you do in college.
I see an interesting question. What is the 0 to 60 time of the rocket? What it's going like, I want to say it's going like 1,000 feet per second by the time it's going up, by the time it's cleared the tower. And 1,000 feet per second is more than 60 miles an hour, I think. Yeah, it's a lot more than 60 miles an hour. So the 0 to 60 time, I would say, is nearly instant. Yeah, these are like, it's hard to really wrap your head around just how fast it is. For reference, it gets to space in about like 2 minutes, I think.
Yeah, it reaches apogee at 2 minutes, so it reaches space before then.
All right, and I think that's the last question we have time for. So I just want to thank again so much RPL for making time to present today. Thank you so much. Thank you for the classes that made time to join us. We will share the recording if you want to watch this again. You can also check out USC RPL's website if you want to see more examples or those videos again. And we hope that you join us for the rest of CS Education Week.
Thanks.